So we're now ready to start Chapter 2, which deals with various types of proof techniques. In Section 2.1, we talk about what's probably considered one of the easier types of proofs, and those are trivial and vacuous proofs. Now, this is only going to apply to certain different types of statements. But if a particular conditional statement, an if-then statement, can be expressed in having one of the following two properties, we can use a trivial or a vacuous proof to prove it. So remember, this is our truth table for an implication or for a conditional statement. We have that an implication of the form P implies Q is only going to be false when the hypothesis P is true and the conclusion Q is false. So notice in particular that whenever the Q part is true, the entire implication is guaranteed to be true. Which means, whenever the conclusion of an if-then statement is true, the entire implication is true. So if you're given an if-then statement and you recognize that the conclusion of the statement is always true, that the hypothesis actually doesn't even matter, that the conclusion is just always true no matter what, then you can use that to justify that the entire implication is true. And we call this a trivial proof. So a trivial proof of P implies Q is one in which we show that the conclusion Q is always true. Right now, this is not normally going to be the case. It's only going to be able to use this proof in a very specific scenario. But if the conclusion is always true, this is probably the easiest way to show it. So let's look at example 1. Let x be an element of n. Remember, this means let x be a natural number. If x is an odd number, then 2 is a prime number. Okay. So let's think through what this is asserting. It's saying if you start with a natural number that happens to be odd, then we can conclude that 2 is a prime number. I mean, that's not actually really saying a whole lot here because 2 as a prime number doesn't even involve that x that you started with. Right? 2 as a prime number is just a fact. We've seen that 2 is a prime number. It's only divisible by 1 in itself, so by the definition of prime, that conclusion is automatically true. Right? So just so that we're clear, this is a conditional statement of the form if P, then Q. If x is an odd number, then 2 is a prime number. And the conclusion, Q, is always true. That means we can use a trivial proof here. Okay, so let's write out what this proof looks like. Now, if your assertion that you're trying to prove starts with an assumption, like ours started with let x be an element of n, our proof is going to start with that same assertion, even if it doesn't particularly matter. Let x be an element of n. Okay, now we can point out that regardless of whether x is odd or even, we don't even really need to bring that into this. All we need to do is explain that the conclusion is always true. Since 2 is a prime number, the conclusion of this statement, is always true. So this conditional statement is trivially true. That's it. That's our entire proof. Couldn't be simpler. When you finish a proof, you put a little box here to indicate that your argument is all done. We've concluded that since the conclusion is always true, the entire statement must be true. Now, notice, I was a little overambitious. I thought I could write that very small. Notice, we didn't make any mention of the hypothesis here. Our hypothesis was that x is an odd number. Right? So in a trivial proof, you don't mention the hypothesis because it really doesn't come into play. 2 is going to be a prime number whether x is odd or even. Okay? So there's no reason to talk about the hypothesis of your conditional statement if you're using a trivial proof. Let's try another example. So example 2. This says let x be an element of the integer. So let x be an integer. If x is greater than 0, then x squared plus 5 is greater than or equal to 0. Alright, so we want to think through, is this actually going to be a statement where a trivial proof could apply? So it's a conditional statement. This is my hypothesis, and this is my conclusion. And I can only use a trivial proof if your conclusion is always true. So is it always true that for an integer x, x squared plus 5 is greater than or equal to 0? Well, yeah, this is always true. Why is that? Well, before we start writing the proof, let's convince ourselves that this is true. We've already shown in the last chapter that x squared is greater than or equal to 0 for all real numbers x. And so also for all integers, right? If it's true for all real numbers, it's certainly true for all integers. And so we can add 5 to both sides here to get x squared plus 5 is greater than or equal to 5. And we know that 5 is strictly greater than 0. So we can conclude that x squared plus 5 is indeed greater than or equal to 0. In fact, it'll be strictly greater than 0, but what we're trying to assert is that it's greater than or equal to 0. So if it's strictly greater than 0, then it's also true to say that it's greater than or equal to 0. Okay, so now we're ready for our proof. Again, we start with any assumptions from the claim. Right, our first assumption here should be let x be an element of z, let x be an integer. Notice that the conclusion of this conditional statement is always true. This is because for any real number, and hence any integer, hence is like thus or therefore, we have shown in past proofs that x squared is greater than or equal to 0. So it follows that x squared plus 5 is greater than or equal to 5, which is greater than 0. Therefore, x squared plus 5 is greater than or equal to 0, and this conditional statement is going to be trivially true. That's the end of our proof. Okay, now a couple of things to notice here, just as a quick remark. This we have shown before. I'm able to just state this as a fact because we proved it during the first unit of the class, that x squared is going to be greater than or equal to 0 for all real numbers. Once you've proven something, you don't need to go ahead and prove it again in another proof. You can just state it as a fact, as long as it's been proven before, okay? So that's going to come in handy in the future as well. Now, the other thing that I want to point out is just like before, notice we did not use the hypothesis. Again, we did not reference the fact that x should be greater than 0, right? The hypothesis of this statement was that x was greater than 0, because we didn't need to. Because it's going to be true if x is greater than 0, but it's also going to be true when x is less than or equal to 0. It's going to be true for every x. So there was no need to specify the hypothesis here. There's no need to even mention it at all. All right, one more example. Let x be a real number, where x is an element of R means let x be a real number. If x squared minus 4 is greater than or equal to 0, then x squared plus 4 is greater than 0. All right, so again, here's our conditional statement. It's of the form P implies Q. And this conclusion is always true for the same reason that the last one was always true, right? Since for any real number, x squared is going to be greater than or equal to 0. Adding 4 to both sides gives me that x squared plus 4 is greater than or equal to 4, which is strictly greater than 0. So we can conclude x squared plus 4 is greater than 0. So this is sort of my scratch work to the proof, just convincing myself that the conclusion is always true. Now I can go ahead and write the proof itself. Start off with the assumption that x be an element of the real numbers. Observe that the conclusion is always true. And that's because we have seen that for all real numbers x, we have x squared is greater than or equal to 0. So it follows that x squared plus 4 is greater than or equal to 4. 4 is strictly greater than 0, and so thus x squared plus 4 will be strictly greater than 0. This is what we were trying to show. We're trying to show that this conclusion must always be true. Now we've explained why the conclusion is always true. And so we can conclude that this statement, this entire statement, this if-then statement, is trivially true because the conclusion is always true. Okay, now that we've seen a few examples, just to wrap things up here and really summarize what we've seen, when you're writing a trivial proof, first you should convince yourself that the conclusion is always true. Then when you write the proof, actually write down any assumptions from your original statement. Explain that the conclusion is always true and give some justification for that. And then wrap it up by explaining to your reader that you used a trivial proof, right? That you were able to show the conclusion is true, which means the entire statement is trivially true, right? This is an important part here, is explaining to your reader just exactly why this follows that the entire conditional statement is true. So you're just letting the reader know this was a trivial proof. Now, related to a trivial proof is something called a vacuous proof. So we had seen that anytime the conclusion is true, the entire conditional statement is true. But that's also going to be the case whenever the hypothesis is false. So when the hypothesis is false, the entire conditional statement is true. Whenever the hypothesis is false, the entire conditional statement is true. Okay, so why does this help? Well, a vacuous proof of a statement P implies Q is one in which we show that the hypothesis P is always false. So if you're given a statement and you can see that the hypothesis is always false, then you don't even have to worry about the conclusion. Okay? You don't even have to mention the conclusion at all. All you do is show that the hypothesis is false and then state that you're proving this vacuously. So as an example, let x be an element of n, that means let x be a natural number. If x squared is less than 0, then x is an odd number. Okay, so this is saying anytime x squared is negative, you can conclude x is an odd number. Alright, well, this is our hypothesis. This is our conclusion. Okay, so is it the case that our hypothesis is always false? Well, yeah, because we've seen that for any real number, and thus for any natural number, that number squared is guaranteed to be greater than or equal to 0, which means it's never going to be negative. It's never going to be less than 0. Right? So our proof is going to look like this. Once again, we start with our assumption. Let x be a natural number. Here's our proof. Let x be a natural number. Notice that the hypothesis, that is x squared less than 0, is always false because any natural number squared is positive, right? Real number squared could be greater than or equal to 0, but natural numbers themselves are positive, so when you square them, you also get something positive. Thus, the entire statement is vacuously true. Okay, so just like before, we wrap it up by explaining to the reader this is a vacuous proof. We've shown the hypothesis is always false, which means the entire statement is true. I also like to point out that we never brought up the fact that the conclusion of the statement was that x is an odd number, because it doesn't matter, right? That could just as easily be x is an even number. The conclusion could be true or false. It really doesn't make a difference, because as long as the hypothesis is false, that entire statement's obviously true, or automatically true. All right, another example, let x be an element of R. If absolute value of x plus 1 is less than 0, then x to the 5th is less than 4. Okay, so here's our hypothesis, P. Here's our conclusion, Q. Is the hypothesis always true here? Well, yeah, it is. Wait, no, it's not. The opposite is always false. If it's always true, that doesn't help us. It only helps us if the conclusion is always true. But no, the hypothesis is always false here, and that's because we know that the absolute value of any real number is guaranteed to be greater than or equal to 0. Okay, so there's no possible way that the absolute value of x plus 1 could be less than 0, because this is going to be greater than or equal to 1. So our proof's going to look like, let x be an element of R. Okay, by definition of absolute value, we know that the absolute value of x is greater than or equal to 0, and so adding 1 to both sides, we get that the absolute value of x plus 1 is going to be greater than or equal to 1. So in particular, it's never equal to 0, and so this means the hypothesis is always false. Always false. And so the entire statement is vacuously true. Again, no need to bring up the conclusion that x squared needs to be less than 4, because it doesn't come into play in a vacuous proof. All you talk about is the hypothesis, right? All you do is explain why the hypothesis is always false in a vacuous proof. All right, now this last one, we have if n plus 1 over n is less than 2, then n squared plus 1 over n squared is less than 4. So here's our hypothesis. Here's our conclusion. Now, this is the first time that we have to think about this a little bit carefully. Why is it that n plus 1 over n is guaranteed to be less than 2 for any natural number n? Well, let's just maybe look at a few cases to try and convince ourselves. When n is equal to 1, this looks like 1 plus 1 over 1 is less than 2. Or 2 is less than 2. This is false. That's good. We want the hypothesis to be false for all n. When n is equal to 2, this looks like 2 plus 1 over 2 is less than 2. Okay, this is definitely also false. 2.5 is not less than 2. When n equals 3, we'd have 3 plus 1/3 is less than 2. This is also false. So this seems false in general, but how do we give a general argument for why that hypothesis is always false? Well, notice that we start off by assuming n is a natural number, which means if we look at this inequality that we're trying to show is false, I can multiply both sides of this inequality by n. I'm going to put parentheses around it just to be clear that the entire left-hand side is being multiplied by n, and the right-hand side as well. And n is positive, which means this is going to not change the inequality symbol, right? You'll still have a less than sign in the middle because you multiplied by a positive. Distributing on the left is going to give me n squared plus n times 1 over n is just 1, right? N over n is just 1, is less than 2n. All right, well, why is this guaranteed to be false? Maybe I can try rewriting this again, moving 2n to the other side. I'll get n squared minus 2n plus 1 should be less than 0. Why is this always false? Well, we can factor this. This factors to n minus 1 times n minus 1. Or n minus 1 squared. In this right here, this is how I know that this statement is false. N minus 1 squared is not going to be less than 0 because any number when squared is greater than or equal to 0. This must be false. Any number squared is greater than or equal to 0. So in particular, it cannot be less than 0. So this is using this argument and working backwards till we get to here is how we're going to be able to show that that hypothesis is always false. All right, so let's try to write this out a little bit more carefully on the next page. Again, what we're trying to prove here is let n be an element of n if n plus 1 over n is less than 2, then n squared plus 1 over n squared is less than 4. We're going to prove this vacuously by proving the hypothesis is always false. So here's our proof. We let n be an element of n because that's our assumption. Notice that we have n minus 1 squared is greater than or equal to 0 because any real number squared is non-negative. So I'm sort of working towards the end of the argument I gave on the last page, and I'm going to just sort of work my way backwards to show that that hypothesis is always false. All right, so expanding this out, I get that n squared plus 2n, n squared minus 2n plus 1 is greater than or equal to 0. I move that negative 2n to the other side to get n squared plus 1 is greater than or equal to 2n. And then I can sort of factor an n out doing the reverse of this step right here. I'm just going to factor an n out to rewrite the left-hand side as n, times n plus 1 over n is greater than or equal to 2n. I can divide both sides by n, which is positive, and I get n plus 1 over n is greater than or equal to 2. This is how we can justify that our hypothesis up here is always false. Our hypothesis is always false, so the entire statement is trivially true. Vacuously true. Vacuously true. That's the end of our argument. So this is our last example, and one thing to point out before I sort of set you off on your own to do some practice is that the hardest part of these is really knowing whether or not you can use a trivial proof or a vacuous proof, because they're not necessarily going to tell you to use that type of a proof. You need to start off by looking at the hypothesis, looking at the conclusion, and asking yourself, is the hypothesis always false? Is the conclusion always true? That's the only scenario in which you'll be able to use either a vacuous or a trivial proof.